Good day, everyone. I am Mr. Franklin P. Calaminas, a PhD Math Ed student of Sorsogon State University School of Graduate Studies. Now I'm going to discuss infinite series, which is one of the topics in real analysis. Now for the outline of the presentation, so here are the topics to be discussed, specifically infinite series, second, the sum of an infinite series, and lastly, the convergent and divergent infinite series. Now, these are the expected learning outcomes. So at the end of this session, it is expected that the students can define what infinite series is. Second, determine the sum of some infinite series. Then, third, identify whether the infinite series is convergent or divergent. Okay, so now let's start with the definition of an infinite series. So if U sub n is a sequence and S sub n is equal to U sub 1 plus U sub 2 plus U sub 3 plus up to plus U sub n. Then S sub n is a sequence of partial sums called an infinite series denoted by the summation of U sub n where U where n equals 1 to positive infinity, and that is equal to U sub 1 plus U sub 2 plus U sub 3 plus up to U sub n plus up to infinity. So that is how we denote an infinite series. But if we're going to equate U sub 1 up to U sub n, that is what we call the sequence of partial sums. Now, by the way, the numbers U sub 1, U sub 2 up to U sub n are the terms of the infinite series. So for an infinite series, we're going to make use of the sigma notation. Okay? And that is annex with U sub n, where the boundaries starts from 1 up to positive infinity. Okay, so now let's have some illustration in which we can differentiate a sequence of partial sums with an infinite series. Now consider the sequence 1 over 2 raised to n minus 1. So given this sequence, so the first term of such sequence is 1 as stated on the slide, then followed by 1 half, 1/4, 1/8, then 1 over 16 up to 1 over 2 raised to n minus 1 as the nth term up to infinity. Now from this sequence, let us form a sequence of partial sums. Now for S sub 1, that is the sum of the first term, so that is equal to 1, or that is U sub 1. Okay? So next we have S sub 2, that is equal to 1 plus 1 half, so the sum of the first two terms, which is equal to 3 halves. Well, for S sub 3, okay, so that is the sum of the first three terms of the sequence, we have 1 plus 1 half plus 1/4, which is equal to 7 over 4. While for S sub 4, okay, so the sum of the first four terms, we have 1 plus 1 half plus 1/4, then plus 1/8, which is equivalent to 15 over 8. Then we have S sub 5, that is 1 plus 1 half up to the fifth term, which is 1 over 16, since we are determining the sum of the first 5 terms of the sequence, which is equal to 31 over 16. Then, what about S sub n? Okay, so that is equal to 1 plus 1 half plus 1/4 Okay, plus 1 8 plus 1 over 16. So listing the first 5 terms of the sequence, then added with up to 1 over 2 raised to n minus 1 as the nth term. So this is what we call, okay, the sequence of partial sums. So based on the definition shown a while ago, so that is denoted by S sub n. What about the infinite series? So with this sequence of partial sums that we have derived, so that is denoted as the summation of 1 over 2 raised to n minus 1, where n equals 1 up to positive infinity. And we just rewrite the sum of the first 5 terms, then added with up to 1 over 2 raised to n minus 1. Since we are dealing with infinite series, so the list, okay, doesn't end with 1 over 2 raised to n minus 1. Okay, but if that is S sub n, or that is the sequence of partial sums, so as stated a while ago, we have to end up with 1 over 2 raised to n minus 1. So for an infinite series, so that should end with plus up to infinity, so with the use of ellipsis. Okay, so that denotes infinity or continuity. Okay, so when S sub n is a sequence of partial sums, so S sub n minus 1 is equal to U sub 1 plus U sub 2 plus U sub 3 plus up to U sub n minus 1. So we just replace, okay, n with n minus 1. So we should end up with U sub n minus 1 instead of U sub n, okay, as the sequence of partial sums. Thus, S sub n is equal to S sub n minus 1 plus U sub n. So this is only a generalization of what we have illustrated a while ago as to the sequence of partial sums. So this indicates that we just add, okay, the sum of the preceding terms, okay, with a particular term, okay, which is denoted by U sub n. So again, S sub n is equal to S sub n minus 1 plus U sub n. Now applying such generalization, okay, so let's have example number 1. So given the infinite series, the summation of U sub n, where n equals 1 to positive infinity, and that is equal to the summation of 1 over n times the quantity n plus 1, where n equals 1 to positive infinity. For letter A, find the first 4 elements of the sequence of partial sums S sub n, and for letter B, find the formula for S sub n in terms of n. Now let's have the solution for letter A. Now based on what we have formulated, okay, which is S sub n, that is equal to S sub n minus 1 plus U sub n. So to find the first 4 elements of such sequence, so we have S sub 1 that is equal to U sub 1. Okay, so the sum of the first term is equal to the first term itself. So that is equal to 1 over, okay, 1 times 2, or that is equal to 1/2. Then for S sub 2, okay, so replacing n with 2 or substituting n, okay, or 2 to n, okay, on the equation S sub n, that is equal to S sub n minus 1 plus U sub n. So that is equivalent to S sub 2, that is equal to S sub 1 plus U sub 2. So this means that we are going to add the sum of the preceding term, which is denoted by s sub 1, with that term denoted by u sub 2, or that is the second term. So we have 1 half plus 1 over 2 times 3. So 1 half, that is the value of s sub 1, okay, based on the first solution. So we have 2/3 as s sub 2, or that is the sum of the first two terms of such sequence. Well, for s sub 3, that is equal to s sub 2 plus u sub 3. Okay, so the sum of the first two terms added with the third term. So 2/3 plus 1 over 3 times 4, that is equal to 3/4. Okay, well, for the fourth, or the sum of the first four terms, that is equal to, okay, s sub 3 plus u sub 4. Okay, so that is equivalent to, okay, the sum of the first three terms, okay, added with, okay, the fourth term. So you have 3/4, okay, based on the third solution, plus 1 over 4 times 5, then that is equal to 4/5. Okay, so with that, the first four elements of, okay, such sequence of partial sums, we have 1 half, 2/3, 3/4, and 4/5. Okay, so we're done with the first task. Okay, so for letter B, okay, so we're going to find a formula for s sub n in terms of n. Now here is the solution. Because u sub k is equal to 1 over k times the quantity k plus 1, so we have by partial fractions, so u, okay, sub k is equal to 1 over k minus 1 over k plus 1. So here we have used the decomposition of partial fractions. So that is the reason why 1 over k times the quantity k plus 1 becomes 1 over k minus 1 over k plus 1. So therefore, so u sub 1, that is equal to 1 minus 1 half, while u sub 2 is equal to 1 half minus 1/3, while u sub 3 is equal to 1/3 minus 1/4. Then that is up to u sub n minus 1, that is equal to 1 over n minus 1 minus 1 over n. Okay, so that is replacing k with n minus 1, so that is the result. While if k is replaced with n, so that becomes 1 over n minus 1 over n plus 1. Now, because s sub n is equal to u sub 1 plus u sub 2, okay, plus u, okay, sub n minus 1 plus u sub n, so that becomes the quantity 1 minus 1 half. So we just replace u sub 1 with 1 minus 1 half as stated, okay, a while ago, plus 1 half minus 1/3 up to 1 over n minus 1 over n plus 1, which is u sub n. Now, upon removing parentheses and combining terms, so we obtain s sub n, that is equal to 1 minus 1 over n plus 1. So as you can see, so the remaining terms are 1, the first term, okay, of u sub 1, which is 1, and the last term of u sub n, which is 1 over n plus 1. Okay, so this means that the formula for S sub n in terms of n, that is equal to 1 minus 1 over n plus 1. Now, by taking n as 1, 2, 3, and 4, we see that the previous results agree. Okay? So it means that if we're going to replace n with those values from 1 to 4, so that would result to the same values, okay, that we have derived on the first task, which is the first element of the sequence, or the first four elements of the sequence of partial sums. Okay, so we are done with the second task, and that is to find, okay, the formula for S of n in terms of n. Okay, so at this point, let's have the sum of infinite series. So here is the definition. So let the summation of u sub n, where n equals 1 to positive infinity, denote a given infinite series for which S sub n is the sequence of partial sums. Now, if the limit of S sub n as n approaches positive infinity exists and it is equal to s, then the series is convergent. And s is the sum of the series. So it means that for us to have an infinite series which is said to be convergent, okay, so the limit should exist, and that is denoted by s, which indicates also the sum of the series. Now, if the limit of S sub n as n approaches positive infinity does not exist, so the series is divergent, and the series does not have a sum. Okay, so it means that if the infinite series is said to be divergent, so the limit does not exist. And it also indicates that the series does not have a sum. Now let's have some illustration for such definition. So the infinite series on illustration 1 is the summation of 1 over 2 raised to n minus 1, where n equals 1 to positive infinity is equal to 1 plus 1 half plus 1 fourth plus 1 over 8 plus 1 over 16 plus up to plus 1 over 2 raised to n minus 1 plus up to infinity. And the sequence of partial sums is S sub n, where S sub n is equal to 1 plus 1 half plus 1 fourth plus 1 eighth plus up to 1 over 2 raised to n minus 1. Now, to determine if infinite series has a sum, okay, so we must compute its limit, and that is denoted as the limit of S sub n as n approaches positive infinity. Now, to find a formula for S sub n, so we'll be using the identity from algebra, which is a raised to n minus b raised to n, and that is equal to the quantity a minus b times the quantity a raised to n minus 1 plus a raised to n minus 2 plus b plus a raised to n minus 3 times b squared plus up to a b raised to n minus 2 plus b raised to n minus 1. Now, applying such identity with a equals 1 and b equals 1 half, so we have 1 minus 2, or rather 1 over 2 raised to n. So with that is equal to 1 minus 1 half times the quantity 1 plus 1 half plus 1 over 2 squared plus 1 over 2 cubed plus up to 1 over 2 raised to n minus 1. Now, that is equivalent to 1 plus 1 half plus 1 fourth plus 1 eighth plus up to 1 over 2, okay, raised to n minus 1. Okay, then that is equal to 1 minus 1 over 2 raised to n over 1 half. Okay, so that is from the equation, okay, derived from using the identity. Okay, so we have to divide both sides by 1 half, and that is from 1 minus 1 half on the right side of the equality or equation. Okay, preceding such equation. Now comparing this equation and the sequence of partial sums, so we obtain S sub n that is equal to 2 times the quantity 1, okay, minus 1 over 2 raised to n. Okay, so if we're going to find the limit of, okay, 1 over 2 raised to n as n approaches positive infinity, okay, so that is equal to 0. So replacing 1 over 2 raised to n with 0, okay, so that becomes 1 minus 0, which is 1, then times 2, okay, so that is the reason why the limit of S sub n, which is 2 times the quantity 1 minus 1 over 2 raised to n is equal to 2. So therefore, okay, the infinite series, that is the summation of 1 over 2 raised to n minus 1, where n equals 1 to positive infinity, has the sum of 2. Okay, so the limit exists and it has a sum of 2. So therefore, it is an example of convergent infinite series. Okay, so now let's have another example. Determine if the infinite series of example 1 has a sum. Now for its solution, so in the solution of example 1, we showed that the sequence of partial sums for the given series is S sub n, that is equal to 1 minus 1 over the quantity n plus 1. So therefore, we're going to find its limit, which is denoted by the limit of S sub n, where n approaches positive infinity, and that is equal to the limit of 1 minus 1 over n plus 1 as n approaches positive infinity. Okay, so the limit of a constant, which is 1, is equal to 1, then subtracted with the limit of 1 over n plus 1, okay, which is equal to 0. So that is the reason why its limit is equal to 1. So the infinite series has a sum equal to 1. Okay, so we write the summation of 1 over n times the quantity n plus 1, where n equals 1 to positive infinity, and that is equal to 1 half plus 1 over 6 plus 1 over 12 up to 1 over n times the quantity n plus 1, then plus up to infinity, which is equal to 1. Okay, so on this example, okay, we have found out that the limit exists, okay, for such sequence of partial sums. So with that, okay, the series, okay, is convergent since the limit exists, which is equal to 1. And 1 also indicates that the sum of the infinite series is equal to 1. So that is how we write, okay, the sum of an infinite series. Okay, so that is equal to 1. Now for the next example, we're going to write with sigma notation the infinite series that is the following sequence of partial sums, which is S sub n that is equal to 1 over 2 raised to n. Then also determine if the infinite series is convergent or divergent If it is convergent, so find its sum. Now let's have the solution. So because s sub 1 is equal to 1 half, okay, so we just substitute n with 1, so that's the reason why s of 1 is equal to 1 half. Then u sub 1 is equal to 1 half. Okay, now if n is greater than 1, so u sub n is equal to s sub n minus s sub n minus 1. So this is from the generalization that we have formulated a while ago, that s sub n is equal to s sub n minus 1 plus u sub n. Now since we are after with u sub n, okay, so that is equated with s sub n minus s sub n minus 1. Okay, after transposing s sub n minus 1 on the other side. Now replacing s sub n with 1 over 2 raised to n, and that is given on the problem, then minus 1 over 2 raised to n minus 1, so we just replace n with n minus 1, and that is the result. Then, okay, solving this two terms, okay, algebraically, so that is equal to negative 1 over 2 raised to n. So therefore, the infinite series is 1 half minus the summation of 1 over 2 raised to n, okay, then n, okay, equals 2 to positive infinity. Okay, so why is that the values of n starts from 2 to positive infinity? Since if you're going to replace, okay, n on negative 1 over 2 raised to n, okay, so that is not equal to 1 half. So we exclude 1 half on such notation. So we start with 2, okay, up to positive infinity. Now because the limit of s of n, where n approaches positive infinity, then that is equal to the limit of 1 over 2 raised to n. Okay, so we're going to make use of the given sequence of partial sums, s of n. Okay, then that is equal to 0. Okay, but 0 doesn't indicate that the infinite series is divergent, since 0 is still a value. Okay, so the limit exists, so therefore the series is convergent, and its sum is equal to 0. So since that is based on the definition that we have encountered a while ago, that the limit of such a series or sequence of partial sums, okay, is the sum of the infinite series. Okay, so now let's continue with this theorem. If the infinite series, the summation of u sub n, where n equals 1 to positive infinity, is convergent, then the limit of u sub n as n approaches positive infinity is equal to 0. So in other words, so we can consider an infinite series to be convergent if the limit of u sub n, okay, as n approaches positive infinity, okay, should be equal to 0. Now let's have an example in line with this theorem. Prove that the following two series are divergent. So for letter A, we have the summation of n squared plus 1 over n squared, where n equals 1 to positive infinity. Then that is equal to 2 plus 5 over 4 plus 10 over 9 plus 17 over 16 plus up to infinity. Then for letter B, we have the summation of negative 1 raised to n plus 1 times 3, where n equals 1 to positive infinity. then that is equal to 3 minus 3 plus 3 minus 3 plus up to infinity. Now for the solution, for us to prove that the following series are divergent, so we need to determine the limit of u sub n where n approaches positive infinity. Okay, so we will use the theorem for us to prove that these series are divergent. Now, having the limit of n squared plus 1 over n squared, since that is the given u sub n for letter A, okay, then n approaches positive infinity. So that becomes the limit of 1 plus 1 over n squared over 1. So that is by dividing each term on both numerator and denominator of u sub n by n squared. Okay, so that is the reason why it becomes 1 plus 1 over n squared over 1. Now, why is that the limit of such simplified u sub n becomes 1? Since the limit of 1 over n squared, okay, is equal to 0, then added with 1, so the sum on the numerator is 1 divided by itself, so the quotient is equal to 1. Now, the limit is not equal to 0, okay? Since for us to have an infinite series which is said to be convergent, the limit should be equal to 0. So in this case, so that equals 1, so therefore it is divergent. So we're done proving the first infinite series as a divergent infinite series. Then for letter B, you have the limit of u sub n, which is equal to the limit of negative 1 raised to n plus 1 times 3, where n approaches positive infinity. So its limit does not exist. Okay, since we have the indeterminate, okay, for negative 1 raised to n plus 1. Okay, so with that, okay, so the given series is also divergent. Okay, so again, for us to consider that the infinite series is convergent, so the limit of u sub n, okay, as part of the infinite series, okay, should be equal to 0. Okay, so we have here another theorem which states that the harmonic series is divergent. So the converse of theorem 8.3.3, okay, so that was shown a while ago, is false. That is, if the limit of u sub n where n approaches positive infinity, that is equal to 0, it does not follow that the series is necessarily convergent. So in other words, it is possible to have a divergent series for which the limit of u sub n, okay, as n approaches positive infinity, that is equal to 0. So an example of such series is the harmonic series, which is in the form of the summation of 1 over n, where n equals 1 to positive infinity, that is equal to 1 plus 1 half plus 1 third plus 1 fourth, then up to plus 1 over n plus up to infinity. Okay, so that is what we call the harmonic series. So clearly, the limit of 1 over n as n approaches positive infinity is equal to 0. But this series diverges, which we now prove as a theorem. Okay, so this is the case in which it contradicts, okay, the theorem being stated a while ago that the infinite series is said to be convergent if its limit or particularly u sub n is equal to 0. So here, okay, its limit is equal to 0. But if we're going to rely or observe the graph on the slide, okay, which is the harmonic series, so it diverges. Okay, so that is the reason why harmonic series is said to be divergent. Okay, so we have here a theorem that involves geometric series, in which states that the geometric series converges to the sum, okay, A over the quantity 1 minus R if the absolute value of R is less than 1. Then it diverges if the absolute value of R is greater than or equal to 1. So those are the conditions to be satisfied, okay, for a geometric series to be convergent or divergent. So an infinite series of the form the summation of A times R raised to n minus 1, where n equals 1 to positive infinity, is equal to A plus AR squared plus up to plus AR raised to n minus 1 plus up to infinity. So that is what we call the geometric series. Okay? So the infinite series that was discussed in illustration 1 and 2 is a geometric series in which the value of A is 1 while R is equal to 1 half. Okay? So now let's have an example in line with such a theorem that involves geometric series. So for example number 5, okay, we are tasked to express 0.3333 up to infinity as a common fraction. So here is the solution. So as stated, we have the sum of 3 over 10, 3 over 100, 3 over 1000 plus 3 over 10,000 plus up to 3 over 10 raised to n plus up to infinity. Okay, so that is the equivalent infinite series of such given repeating decimal, in which the repeated digit is 3. So this is a geometric series in which A is equal to 3 over 10, while the common ratio, which is denoted by R, is equal to 1 over 10. Now, because the absolute value of R is less than 1, okay, so based on the theorem that you have encountered on the previous slide, so the series converges. And its sum is A over 1 minus R. So therefore, okay, replacing A or substituting A with 3 over 10 while the common ratio or R is equal to 1 over 10. Okay, so that becomes 1/3. Okay, so that is the common fraction, okay, that will be equal to 0.333, okay, up to infinity as the given repeating decimal. Okay, okay, so we have here another set of theorem in which, okay, that involves a non-zero constant denoted by C, in which on the first statement, if the series, the summation of u sub n, where n equals 1 to positive infinity, is convergent, and its sum is represented by S, okay, then the series, the summation, okay, C times u sub n, where n equals 1 to positive infinity, is also convergent, and its sum is the given constant, okay, and to be multiplied by the sum of the given infinite series. Okay, so in other words, if the given infinite series is convergent, and that is being multiplied, okay, by a non-zero constant, still the infinite series is convergent. And we just multiply that non-zero constant with the sum of the given infinite series. What about for the second statement? So if the series, the summation of u sub n, where n equals 1 to positive infinity is divergent, then the series, the summation of u sub n, where n equals to 1 to positive infinity is also divergent. Okay? So that is the same with the first statement. The only difference is that here, the given infinite series is said to be divergent. So therefore, once the given infinite series is multiplied by a non-zero constant, so that is also divergent. Now, in connection with such theorem, so let's have an example. So here in example number 6, we're going to determine whether the series is convergent or divergent. So given the infinite series, the summation of 1 over 4n, where n equals 1 to positive infinity. So for the solution, so we're going to write, okay, the first four elements, okay, of the infinite series from 1/4 as the first term, followed by 1/8, 1 over 12, 1 over 16, up to 1 over 4n, okay, so that is for the nth term, plus up to infinity, okay. Now, because the summation of 1 over n, okay, where n equals 1 to positive infinity, is the harmonic series, so we have encountered it on the previous slides, and based on the theorem, okay, so harmonic series is divergent. So based on the previous theorem that we have encountered a while ago, okay, so if the given infinite series is divergent, okay, and that is only multiplied by a non-zero constant. So let's say, for example, on this case, so the constant is equal to 1/4, okay, so the given series is divergent, okay. Okay, so now let's have a theorem in which that involves the sum of, okay, convergent and divergent infinite series. So we have here on the first theorem, it states that if the summation of a sub n, where n equals 1 to positive infinity, and the summation of b sub n, where n equals 1 to positive infinity, are convergent infinite series whose sums are s and t respectively. So, okay, so for number 1, we have the summation of a sub n plus b sub n, where n equals 1 to positive infinity is a convergent series, and its sum is s plus t, okay. So that is how we denote the sum of two convergent infinite series, okay. Then for number 2, we have the summation of a sub n minus b sub n, where n equals 1 to positive infinity, is also convergent series, and its sum is s minus t, okay. So that is only true if both infinite series are convergent, okay. So let's have the next theorem. So it states that if the series, the summation of a sub n, where n equals 1 to positive infinity, is convergent, and the series, the summation of b sub n, where n equals 1 to positive infinity, is divergent, then the series of the summation of a sub n plus b sub n, where n equals 1 to positive infinity, is divergent. Okay, so here is the case in which if we're going to have the sum of a convergent and a divergent infinite series. So the result is a divergent infinite series. Okay? Okay, so now let's have an example in connection with such a set of theorems. So for example number 7, we are tasked to determine whether the series is convergent or divergent. So the summation of 1 over 4n plus 1 over 4 raised to n, where n equals 1 to positive infinity. So for the solution, so we have already found out on example number 6 that the series of the summation of 1 over 4n, where n equals 1 to positive infinity, was proved to be divergent. Okay? Since that is a harmonic series being multiplied by a constant 1 over 4 or 1/4. Now, because the series, the summation of 1 over 4 raised to n, where n equals 1 to positive infinity, is a geometric series with the absolute value of r is equal to 1/4, okay, which is less than 1. So it is convergent. So that is based on the theorems that we have, okay, involving geometric series, that if the absolute value of the common ratio is less than 1, so it is said to be convergent. Okay. Now, applying what we have learned on those theorems on the previous slide, okay, involving the sum of convergent and divergent infinite series, so the result is divergent. Okay, so that is the reason why on the last statement here, hence the given series is divergent. Okay, so we have here another theorem which states that if the summation of a sub n, where n equals 1 to positive infinity, and the summation of b sub n, where n equals 1 to positive infinity, are two infinite series, differing only in their first m terms. Okay, let's say for example a sub k is equal to b sub k if k is greater than m, then either both series converge or both series diverge. Okay, so for us to further understand the given theorem, so we will have an example, okay, in line with such theorem. So here we're going to determine whether the series is convergent or divergent. Now, given the infinite series, the summation of 1 over n plus 4, where n equals 1 to positive infinity, so for its solution, so on the first step, so the given series is 1/5 plus 1 over 6 plus 1 over 7. So that is based on the given u sub n. We will replace n with 1 up to 3. So that is the reason why we have listed 1/5 plus 1 over 6 plus 1 over 7 plus up to 1 over n plus 4 as the n term plus up to infinity. So which can be written as 0 plus 0 plus 0 plus 0 plus 1/5 plus 1 over 6 plus 1 over 7 plus up to 1 over n plus up to infinity. Okay? Now, the harmonic series, which is known to be divergent, is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1 over 6 plus 1 over 7 plus up to 1 over n plus up to infinity. Okay, so as you can see, so this is an application of the stated, okay, theorem above. So we have here the first four terms. Okay, we have use zeros as the first four terms. Okay, so given the infinite series 1 over n plus 4. Okay, so that is similar to harmonic series. Okay, in which the first four terms are 1 up to 1/4. Okay, and we have 1/5 up to infinity. Okay, which is similar, okay, to the given series. So with that, okay, series for the given series differs from the harmonic series only in the first four terms. Okay, so with that, since harmonic series is divergent, so the given infinite series is also divergent. Okay, so now at this point, for you to apply what you have learned on our discussions on the previous slides regarding infinite series, the sum of infinite series, and other theorems in which that involves convergent and divergent infinite series. So here are some of the practice exercises. So for number one, you're tasked to find the first four elements of the sequence of partial sums S sub n and find the formula for S sub n in terms of n. So also determine whether the infinite series is convergent or divergent. Then if it is convergent, find its sum. Okay, so that is the given infinite series for number one. Well, for number two, you are tasked to write with sigma notation the infinite series that is the given sequence of partial sums. Also determine whether the infinite series is convergent or divergent. If it is convergent, find its sum. Then lastly, we have to express the non-terminating repeating decimal as a common fraction. So on the previous discussions, we have 0.333, okay, as the given non-terminating repeating decimal. So here we have two digits being repeated, which is 27 or 2 and 7. Then determine whether it converges or diverges to its sum. Okay, so here is the reference I have used for our discussion for infinite series. So that ends my discussion regarding infinite series, which is one of the topics under real analysis. So once again, this is Mr. Franklin P. Calaminos, a PhD Math Ed student of Sorsogon State University School of Graduate Studies. Thank you for listening and God bless you always.